All right, today we're cracking open the Calculus Toolkit. We're going to get to the heart of one of its most powerful abilities, figuring out how functions actually behave. So, let's just jump right in.
I mean, this is one of the big questions in math, right? You look at some equation, some function, and how in the world are you supposed to know what it's going to do? Is it just going to shoot up to infinity? Or maybe it'll level off somewhere? Or will it just, bounce around all over the place?
Okay, so take a look at this. At first glance, this thing looks like an absolute mess, doesn't it? I mean, it goes up, it goes down, it's flying off in all these different directions. If you don't have the right tools, trying to describe what's happening here feels, well, pretty much impossible. But here's the thing, it's not.
And that's because, luckily for us, mathematicians have spent centuries coming up with this incredible set of tools. They're designed for one specific job: to decode this kind of behavior, to find the hidden patterns, the order inside what looks like total chaos.
So that's what we're going to do today. We're going to build our very own Calculus Toolkit. We'll pull out each tool one by one, figure out exactly what it's for, and then see how they all fit together to make sense of even the craziest looking functions. First up in our toolkit, we've got the limit laws. Now, I want you to think of these as our precision instruments. They're like the magnifying glasses and tweezers of our kit, the things that let us zoom way in on a single point of a function and see exactly what's happening at that one tiny spot.
Okay, first tool out of the box, the sum law. And the idea here is, well, it's just so simple and elegant. It says the limit of two things being added together is just the sum of their individual limits. It's fantastic. It lets you take one big, intimidating problem and just break it into two smaller, much easier pieces.
And right next to it, you've got the difference law. And yeah, no surprises here. It works exactly the same way, just for subtraction instead of addition. Simple as that.
Then we have the product law, which keeps this same powerful idea going. The limit of a product, you guessed it, it's just the product of the limits. We're still doing the same thing, breaking a big problem down into smaller, bite-sized chunks.
All right, now for the quotient law. This one handles division, and it comes with a little bit of fine print, a really important warning label. It works just like the others, but you have to make sure the limit of the bottom part, the denominator, isn't 0. And that makes total sense, right? It's the one rule we can never, ever break in math. You just can't divide by 0.
Next, we've got the power law, which is another awesome shortcut. Basically, it lets you take the limit inside the exponent. So, you figure out the limit of the main function first, get that number, and then you raise it to the power. It just makes the whole process so much cleaner.
And to round out our precision tools, there's the root law. It works pretty much just like the power law. You can pull the limit inside the root symbol. So find the limit of what's inside first, and then take the root of that result. Just got to be a little careful with even roots. Like square roots. The number inside has to end up being positive.
Okay, so we've laid out all our precision instruments on the workbench. Now, let's stop just looking at them and actually put them to work. Let's see how they all connect to solve a real problem.
All right, check this thing out. We're going to find this limit. Now, we're not going to try to solve this whole beast at once. No way. We're going to use our toolkit step by step. First thing we do, we grab that quotient law to split the top from the bottom. Cool. Now we have two smaller problems. Then we use our sum and difference laws to break those down even further into individual little terms. After that, the power and constant multiple laws let us get right down to the variable x. And once we've broken it all down, then we can just plug in the numbers and simplify the whole thing. And when we follow that system, what do we get? 1/4, see? It's just a methodical process of making a big problem small.
So you see, the limit laws are all about that super zoomed in, microscopic view. But what about the big picture? What happens when a function just keeps going and going forever? What's its long-term behavior? For that, we need to pull a whole different set of tools out of our kit.
And those tools are called asymptotes. The best way to think about these is like guardrails on a highway or invisible boundary lines for the graph. They're not about what's happening at one specific point. Nope, they tell us about the function's overall shape and where it's headed in the long run.
So what is an asymptote formally? It's a line that the function's graph gets closer and closer and closer to, but it never actually touches or crosses it. It's like a path that the function is drawn towards as it heads out towards infinity.
So, there are three main types of these guide rails that we're going to add to our toolkit, and each one tells us something unique about how the function behaves.
This little comparison chart really sums it up. A vertical asymptote, that tells you what x values are forbidden territory, the spots that make the function just blow up and shoot off to infinity. A horizontal one,
That answers the question, what y value does this thing eventually settle down to? And a slant or oblique asymptote, that tells you if the function is basically just following a straight, sloped line as it gets really big.
Finding vertical asymptotes is usually the easiest place to start. Seriously, if you have a function that's a fraction, just look at the bottom part. Figure out what x values make that denominator equal to 0. Those are your danger zones. They create these vertical walls that the function gets really close to but can never ever break through.
And this graph is a perfect example. See that dashed line right there at x equals 2? As the curve comes in from the right side, whoosh, it shoots straight up to positive infinity. And when it comes in from the left, it dives down to negative infinity. It gets unbelievably close to that line, but it will never ever touch it.
Now, for horizontal asymptotes, it's all about comparing degrees. And by degree, I just mean the biggest exponent on x you can find. So you look at the top and the bottom of your fraction, and it's a simple three-way comparison. Rule 1, if the top's degree is bigger, nope, no horizontal asymptote. Rule 2, if the bottom's degree is bigger, the function will always level out at y equals 0. Easy. And rule 3, if the degrees are the same, you just take the numbers in front of those terms, the leading coefficients, and make a fraction out of them. That's your asymptote.
Okay, and then there's the special case, the slant or oblique asymptote. This one's kind of cool because it only shows up under one very specific condition, when the degree of the numerator is exactly 1 bigger than the degree of the denominator. If you see that happening, you know you've got a slant asymptote. And to find its actual equation, you got to break out an old tool, polynomial long division.
So let's go all the way back to that chaotic graph we saw at the very beginning. It doesn't look so random now, does it? Now that we have our toolkit, we can see exactly what's going on. We can spot the vertical asymptote there in the middle, totally dictating what happens. And as x gets huge in either direction, look at that. The function is just hugging that dotted slant asymptote. Our tools totally uncovered the hidden structure.
So there you have it. From the super precise limit laws to the big picture guide rails of asymptotes, you now have the basic toolkit for understanding how things change. It's an incredibly powerful set of ideas. So the only question now is, what hidden behaviors are you going to uncover out there in the world?